everyone, this is Miss Krupstadt, and we're going to do a quick lesson on 7.4, which is finding and factoring out the greatest common factor. You may have heard that word before, or that phrase. If not a big deal. I know you have seen this in middle school at some point, but they might not have called it the greatest common factor. What we're going to be looking for today is the biggest term that all of the terms have. All right, so it'll make a little bit more sense. So when we look at an example like this, I have two groups. Group 1 has 3 stars, 5 smiley faces, and 2 arrows. Group 1 has 2 stars, 3 smiley faces, and 4 arrows. And what we're asking is, what do they have in common? And you probably would think, well, they have stars, smiles, and arrows in common. But more specifically, they each have 2 stars. I could not say they each have 3 stars, right? Because group 2 doesn't have 3 stars. They both have 3 smiley faces. I couldn't say any more than that because group 2 doesn't have more than 3 smiley faces. And then in terms of arrows, they both have 2 arrows. That's the GCF. That's the greatest thing that they all have in common. What we're going to be doing this with today is numbers and variables. So the first example here, we're going to find the greatest common factor of 12, 36, and 20. So I'm going to start by just thinking about what are the factors of 12, 36, and 20. This is very similar to what we're doing with our box method, where we're coming up with magic numbers. So I'm going to list out every possible pair of numbers that will multiply to 12. 1 times 12, 2 times 6, and 3 times 4. Let's think about that same thing with 36. We have 1 times 36, 2 times 18, 3 times 12, 4 times 9, and then 6 times 6. And for 20, we have 1 times 20, 2 times 10, and 4 times 5. Now, when I'm looking across these, I want to find the biggest one of those that they all have in common, the biggest number. So if I started by looking at 12, okay, I notice I have a 12 in my 36 list, but I don't have a 12 in the 20. So 12 is not the greatest thing they all have in common because 20 doesn't have one. If I look at 6, I see a 6 in the 36 list, but I don't see it in the 20 list. So 6 is not a common factor. If I look at 4, I have 4 in the 12 list, 4 in the 36 list, and I have 4 in the list with 20. So 4 is a common factor. Now, it's not the only common factor. They all have 2s, they all have 1s, but 4 happens to be the biggest common factor. So the GCF of 12, 36, and 20 is 4. Let's look at this with variables. All right, we have x to the 8th, x to the 6th, and x to the 5th. Now, this is a little bit harder to come up with factor pairs, but we could just write it in expanded form where we're listing out all of the x's that multiply to give us that power of x. So, for example, for x to the 5th, I know I have x times x times x times x times x. 5 x's multiplying with each other. Now, this is more similar to when we were looking at shapes. What do they have in common? What is the most number of x's that they all have? Well, this one has 5 x's, this one has 5 x's, and this one has 5 x's. I could not say they all have 6 x's in common because the last one doesn't have it. So in this case, our GCF would be x to the 5th. That is the most x's that they all have in common. We're going to put that together and do an example in our notes. So if you don't have your notes out, make sure to get them out. All right, so a greatest common factor, or GCF, is the largest factor that the terms all have in common. And in particular, if you wanted something for variables, it is the smallest exponent for each variable. So an example of this, 10x to the 2nd, y to the 8th, 12x to the 5th, y, and 20x to the 3rd, y to the 2nd. Now notice we have variables and numbers in here, but we're just going to look them kind of separately from each other. So let's start with 10. 1 times 10 and 2 times 5. 12 is 1 times 12, 2 times 6, and 3 times 4. And 20 is 1 times 20, 2 times 10, and 4 times 5. I'm going to look across the list and see what they all have. Well, they don't all have a 10 because 12 doesn't have a 10. They don't all have a 5, so that's not going to work. But I do see that they all have a 2. So 2 is my greatest common factor, or part of it. Next, we're going to look at our x's, and I lost my ability to change my, oh, there we go, to change my color, but maybe I can. Oh, I can. So when we look at our x's, I have x to the second, x to the fifth, and x to the third. If you think about how many are actually in each problem, x or term, x to the second is the smallest exponent, or the smallest number of x's that each of them have. And then when we look at our y's, we have y to the eighth, y, and y to the second. Remember, there's just this imaginary little 1 on that middle y, so the smallest number of y's we have is just y. So our GCF here would be 2x to the second and y. What I'd like for you to do now is pause this video and try this problem. You could do it on the scratch paper in the back of your packet. Try to see if you can come up with the GCF for these two terms. Hopefully you got 32x to the fifth. This one's kind of fun because it actually ends up being quite a big number, 32. And then x to the fifth because the smallest exponent that they both have is 5, so x to the fifth. Let's try another one on the back of your packet. This time I have three terms, 5x to the third, y to the second, 11x, and 21x to the fourth y. Come up with the greatest common factor for these three terms. This one's also a fun one. 1 is the number that they all have in common because both 5 and 11 are prime numbers, so they don't have a lot of factor pairs. And then it's also fun because you'll notice that they all have x's, and the smallest they have is x to the first, but they do not all have y's. Only two of the terms have y's, and so since they don't all have it in common, it is not part of our GCF. We're going to move into a similar and yet kind of different topic. What we are going to be doing with problems is we are going to factor them, which means we are going to be splitting them up into something that looks like this, or looks like multiplication. I would compare this to what we were doing with the box method, where we would have two binomials multiplying with each other. This is just an example. Okay, but this time, instead of having a binomial times a binomial, we have a monomial times a trinomial. Okay, this is our monomial, and this is our trinomial. You have seen problems that look like this already, and traditionally what we do is we will distribute that 2x and multiply it with all the terms inside the parentheses. So that would give us 2x to the fourth minus 8x to the third plus 6x. What we're doing today, though, is we are going the opposite direction. So I am going to give you a problem that has no parentheses in it, and I am going to have you go the opposite direction. Well, if we multiply to go forward, what operation do you think we're going to do to go backwards? We will end up using division. And 2x, this monomial out in front, is going to be our GCF. All right, let's do an example, and it will make a lot more sense as we go. So the problem that we're going to do as we work through this process is going to be 10x to the fifth plus 4x to the third minus 2x to the second. Now you'll notice instead of putting commas in between my terms, I do have adding and subtracting. This is a polynomial, so my final answer is going to be a polynomial as well. First thing we're going to do is think about our factor pairs. 1 times 10 and 2 times 5. 1 times 4 and 2 times 2. And then 1 times 2. All of them have a 2. So part of my GCF is 2. And then the smallest power of x that we have We have x to the fifth, x to the third, and x to the second is x to the second. So our GCF is 2x to the second. What we want to do is we want to take that 2x to the second away from every single term. So we're going to divide each of our terms or our entire polynomial by our GCF. So I am going to literally set up little mini division problems, 2x to the second, 2x to the second, 2x to the second, and I'm going to divide to see what I'm left with. When I do my division, I am going to think about it in two little baby steps for each one of these. So the first one I have, I'm going to think about 10 divided by 2. 10 divided by 2 is 5. Then I'm going to think about the variables, which now I'm having a hard time switching my color. There we go. The x to the fifth divided by x to the second. If you recall, when we did exponent properties, there's a property you can use. But if you forget, we're really taking x to the fifth, or 5x's, and dividing by x to the second. And so we get a couple cancelizations. Is that a word? Cancellations. So we're left with 5x to the third. Now, in honor of our time, I'm going to stop switching between highlighters and pens, so I'm just going to work with this. So in this next one, I have 4 divided by 2, which is 2. And then for the x's, I have x to the third divided by x to the second. So we get that cancellation, which leaves me with just an x. Or I can subtract my exponents. And then in this last one, I have negative 2 divided by 2, which is negative 1. And I have the x to the second divided by x to the second, and so all the x's end up canceling out. So I'm just left with that minus 1. The x's cancel and don't have to be written anymore. So our final answer here is we did divide out that 2x to the second, and when we divided that out, we were left with 5x to the third plus 2x minus 1. This is our final answer. We will have the GCF out in front and what we're left with after we divide on inside the parentheses. Here are a couple reminders, an example we're going to do to kind of demonstrate some of them, but things to remember. First, and this is new, if the first term is negative, we don't want to leave that negative there. We are going to factor out that negative number. And I'll show you what that looks like in our try this problem. The second note here is make sure that there's nothing else that can be taken out of the parentheses. So if I go back to this last problem that we did, 5, 2, and 1, there is nothing that they have in common. So I know that I'm going to be done there. And then the last one, you can always check your answer by doing multiplication or distribution to see if you can get back to the original problem. All right, so let's look at the one that we have here. I have negative 12x to the fifth, y to the third, minus 6x to the fourth, y to the second, plus 3x to the second, y. Let's start by looking at our GCF. So if I think about 12, I'm not even going to worry about the negative yet. I'm going to write out my factor pairs. Then I have 6, which is 1 and 6, and 2 and 3, and I have 3, which is 1 and 3. Well, 3 really doesn't have a lot of options, but it does so happen that every single one of these has a 3. So part of my GCF is going to be, oops, not what you write, thank you. Nope, still not going to write, okay. GCF is 3. And then when we look at our variables, the smallest x we have is x to the second, and the smallest y we have is y. Now, in order to factor out, I am going to divide each of these terms by our GCF, except for there's one thing I'm going to have to be careful of, which is the fact that I have a negative in the front. The way we get rid of a negative in the front of our polynomial is we will divide by a negative. So instead of a GCF of a positive 3, we're going to use a negative 3. That's going to leave us with that negative 3x to the second y as our GCF. Then I'm going to do little mini division problems. So I'm going to get negative 12 divided by negative 3, which is positive 4. If I have x to the fifth divided by x to the second, that leaves me with x to the third. And then y to the third divided by y to the first is y to the second. That's all of the parts of that first term. I'm going to do the same thing with these next two terms. Negative 6 divided by negative 3 is a positive 2. X to the fourth divided by x to the second is just x to the second. Y to the second divided by y to the first is just y. Now you might be tempted in this last one to just close your parentheses because they look like the same thing on top and bottom, but we cannot do that. We still have to do division. So 3 divided by negative 3 is negative 1. X to the second divided by x to the second cancels, and y divided by y cancels. It is really important to still write that negative 1 because if I wanted to, check. If I wanted to, you do not have to. I should be able to distribute in order to get back to the original problem. And if I didn't put that minus 1 there, I wouldn't be able to get back to that original problem. But here is our final answer, where we have our GCF out in front and what we have left after we divide inside the parentheses. All right, so now I would like for you to do some practice. You have page 12 in your note packet that you can do, and you also have some Savas or Easy Bridge practices that you could do on the computer using your scratch paper or scratch paper I have in the classroom. Please commit to doing something so that you are practicing, even if that means going back and doing some of the box problems from earlier sections. I will be back on Friday to help you and answer any questions that you might have. Have a great Thursday!